No, we can't get the block up high enough. No, doesn't seem to be working. Jumping on the block. Yeah. Obviously, we can't jump on the block, then pick it up and pull it up. We're not that nimble. Okay. One more try on the right, just in case I need, like, just the right launching angle or something. Oh! That worked. Okay. That felt iffy enough that I'm not sure if that's the intended solution, but I'm going with it. Hello everyone, and welcome back to Portal Reloaded. The test chambers are getting more and more difficult here, and very luckily I forgot to save after last week's episode, but we can skip ahead with the map select to right where we should pick up. So, let's see what we have in store for us now.
You are in the home stretch now. Only a few more chambers until this testing course is over. Time to introduce the last new testing element.
Okay.
These aperture science excursion funnels will mostly work in both timelines. Have fun exploring all your options in the next chamber.
So this looks new. It's been a while since I played through all of Portal 2, but I don't seem to remember seeing this there. Okay, so basically it kind of sucks you in and then pushes you along. Okay. So I'm just trying to think of the physics of how this would work. From a real-world perspective, you could get something like this just by blowing air very quickly. Yeah, you have wind tunnels, you can go and play in one if you want. There are plenty of things set up like that. The tricky part is that this actually sucks you in, whereas if you have a draft of air, it tends to spread out. So the difficulty here is setting up something that will be contained in a tube. And I wonder how you might be able to do that. Maybe you could do something like that with a magnetic field, but then it would, again, it would only work on things that are magnetic, and getting a magnetic field over this distance is very difficult. So, yeah, I think something self-contained like this would be well outside of what we can do with current technology. There might be some trick we can do if, yeah. I'm just trying to think. You know, the best thing we have to keep things contained is lasers. Even those spread out a bit. It's just the way the laws of physics work is that you can't compress something to reliably go in a straight line. It actually goes down to quantum mechanics that the uncertainty principle actually says you can't be certain enough it's traveling straight. So as it travels along, any beam will inevitably spread out. Now, if you have something at the receiver to collect it, I mean, that can help. You can do that with magnetic fields to get something relatively straight, but still not perfectly. It's gonna bulge out a bit at the sides. So, yeah, I don't think we can do this. Yeah, sorry to burst your bubble, Aperture, but, yeah, some of your inventions might not actually work. I'm not sure if you're aware. Okay, well, let's have a go anyway. So, excursion funnels. Okay, so there's a grating here, which we can't pass through, but presumably the funnel can. It pushes us up slowly, and we can push ourselves off. Okay. So that's basically how it works. Let's see how things look in the future. Okay. Funnel still being created here. And we have an exit over there. Emancipation grill there. Alright. block up there. Probably a switch that we can't see for it. Let's just check, is that the same in the present? Yes. Okay, so up there we have another grill. We could put that up. Wrong portal color. So, yeah, we can put one across there, or switch the sides, push it the other way. Oh, but I think these two, yes, where they would be will cross. So we can push ourselves up, and then when you get to that height, oh, too soon. When we get to that height, we can put up another there to push ourselves across. Yep. There we go. Hit the switch. Get a cube. Okay. And then we can do the same thing going the other way to put the cube over there where I think there's a switch we can stand on. So we want to put it like that. Let it go over there, then we'll do the same ourselves. And put the block on the switch. Okay, so when the block is on the switch, we have changed from blow to suck. So we are shooting out a funnel which blows stuff, which sucks things into it. Okay. So if we were to, for instance, put it down there, it'll pull us through, but yeah, we hit the grate, can't go further. Or we could put it on the ceiling and get sucked up. Now, we cannot shoot through there because we don't have a clear line of sight to it. Now, interestingly, we haven't used the time portal yet, so I suspect that's going to come into play in solving this, but let's just go around a bit. Okay. Now, from here, we do... Yeah, okay, so we can set it up there. The problem is... Okay, two problems. Problem one, when we're up there going through it, we'll ourselves go through that grill, which will destroy all existing portals. So we better not do that until we have everything we need up there. Problem two is getting up there, but that might be solved just by going into the future and picking up the block from here. So let's reset. Let's go over, collect that block. Okay. So we can now take this back to the present, which will allow us to place it over there. So what I'm thinking is, in the future, we can redirect that as we wish. So it's coming out. So let's make it come out there, and then time portal through. So then we have a funnel going up there. And yes, I think we can just go through while holding the block. Ooh. And there's our problem. The Emancipation Grill destroys the block. Okay. Yep, I forgot about that. So we haven't quite solved this. Okay, so in order to complete this, we will have to have a block here. How can we get a block here? So we can't bring it through the grill. we can't bring it through here since there is a grid or fence over it, whatever you call that. So, is there any wall set up that would allow us to push it through? Huh. Okay. Does that grid exist in the future? Yes, it does. Okay. Alright, let's check things out in the future, see if anything's a bit different here. That might, in a way that might help us. Okay, still grids there. Okay. No, I'm not seeing anything that obviously helps us. Okay, let's just set things up in the present again. So we've got the block there, but the future one has been destroyed. We're going to need to recreate it. So let's go. We can just nab that, jostle it, put it back into place, and then the future one will exist again. So let's do that, and then we can think about solutions for getting the future one where we need it. Okay, so I suppose we could have also gone and hit the switch in the future to get a new block. That would have worked as well, but, well. Okay. Got this in the future. And then we can do same thing so that we have the two funnels, or expulsion tubes, whatever you call them, in the future. Okay, let's check this for any hints. Okay. Yeah, I'm not seeing anything obvious there. Alright. Let's have a look around the room and think. How do we get the block up there? So the block is a bit more flexible than we are with how we can move it. If we can get ourselves close, like for instance, if we could stand up there, we could jump up and place the block up there. So we don't need a path that gets the block all the way up there. We just need one that gets it close enough. So let's see, if we jump out of that funnel, how far do we get? Do we get close enough to that other ledge? Not quite. Okay. So I don't think that's it. Now, can we do anything with conservation of momentum? I mean, we could, well, not conservation, but non-conservation, or that is, shooting through a portal to get momentum up. So, first thought, yeah, imagine we don't have this expulsion tube. We could, well, we could have the tube, then while we're up in the air, shoot a different portal down, and then we'll fall, go through that different portal, and come shooting out. That might work. I'm just trying to think, is there any place we could put the other portal? But I'm not really seeing any good launch points. Now, one thing I'm noticing, that this area, there's a step out here, and I'm wondering if that's deliberate. There are a few ways that might be deliberate. Maybe it's so that, like right here to across, we have portals that we could set up and have a straight line between portals. We could also do that at the entrance. I'm not sure if that's necessary. let's see. Yeah. Yeah, it could just be a room design choice. They cut out to let us see the door there. No. Okay. So if we put that going the other way, yeah, it breaks things in the future. But I'm just thinking if we do go that way, and we'll just hop back over to the future. Ah. Okay. Okay, why do you always move me out on the second time through? Okay. Yeah. Yeah, we're going like that, and then we do blue there, through the time portal, go up, and then when we're on the way... Okay, I'm not sure why. Let's try that again. Then when we're on the way over here, we could push ourselves off and maybe land there? No, okay. I'm not even sure if that would be useful to us. Alright. So, let's work backwards. We need to be up there ourselves. We figured out how we can do that, but it involves going through this grill. We also need to have the block up there, and we cannot take the block through the grill. So, how do we get the block up there? So, there are openings on either side. On the right, it looks like this ledge is close enough that if we get up there, we can pick up the block, jump off, and lay it. So, and I don't see any other way we could set something up to get up there. So for now, I'm going to focus on that option. But how do we get to that option? So let's test this extraction funnel. Can we just jump into it? Okay. Kind of lose it to us. We can get up and place the block there. Okay, so we can reach up, we can place the block there. That is maybe closer to solving the problem. Maybe not, but we can't get out of this ourselves. We have control to go left and right from this one, but that's it. Okay, so what do we do from here? Now, we could set the things up at top so that we're pushed over to the right. If we stand there, can we make a jump? It's worth a try. So, let me set that up and figure it out if that works. Yeah, that looks too far for a jump. I mean, it's a bit closer when we're pushing ourselves out of this, but when we're just on the ground here... Oh, yeah, I jostled it. Wait, we'll deal with that later. Right now, let's just play around, figure out a solution for getting over there. Okay. Yeah. Alright, so option 2, you've got blah blah blah. Alright, need to... Alright, I'm gonna need to fiddle a bit here. Okay. Okay, now have the future cube again. And so let's just set things up so that we have the future tube again. Okay. We get up here and we push off. Yeah, we're not getting particularly close. Yeah, even if we go at an angle. Okay, that does not seem to be the intended solution. We could maybe... Yeah, we can put the block up there, but we can't get there ourselves. So, what to do? Alright. Okay, you know what? I'm just going to pause the recording here while I think about this, and if and when I come up with any new ideas, I'll show you when I test it out. So, be right back. Okay, first idea worth checking. What if we go up here, we set up a portal that will come out from there by shooting around here. So what if we take that up and then instead of going through the extraction grill, we push ourselves off to the side? Can we get onto the ledge from there? So we'll need to set things up in the future again. Okay. Now I need to be careful not to get too close. No, I think we're still too far away. It didn't look like we were getting close at all. Can we maybe get to the ledge on the left, just in case that's useful? Okay, we can get to this ledge. So, in case any solution we come up with relies on this, we know how to get here. Yeah, I'm not sure this will be at all useful, but it is a thing we can do. I just want to try it with the other direction one more time. It did feel a bit close, but okay, let's try it on the left. See how close we are to jumping up and putting the block up. No, we can't get the block up high enough. No, doesn't seem to be working. Jumping on the block, yeah, obviously we can't jump on the block, then pick it up and pull it up. We're not that nimble. Okay, one more try on the right, just in case I need, like, just the right launching angle or something. Oh, that worked. Okay, that felt iffy enough that I'm not sure if that's the intended solution, but I'm going with it. There we go.
The time-bending technology used to create these time portals is only stable in one specific configuration. We cannot choose the exact point in time to which the time portals will lead. We can only take a small glimpse of what the facility looks like 20 years from now. What exactly transpired is still unknown, but the data we collected points to a single rogue test subject.
I still say improper maintenance is the explanation. That's a lot simpler. Yeah, so I wonder if the way they're setting this up is maybe right now we're a bit before the events of Portal 1. Although, Now, in that case, wouldn't GLaDOS be around if this were before Portal 1? Why isn't GLaDOS the one talking to us? Yeah, I know outside of game they couldn't hire that voice actress. In game, I wonder what the explanation is. Okay. Test chamber number 24. Getting close to the end now. Okay. Cube comes out, bonks you on the head. Where does it come out? Over there. Okay, gets out, caught in that tube. Gets pushed over to there. Oh, not all the way to there. It gets caught on that screen. Okay, so what did these two switches do? This one... Oh, so interestingly, the exit is right here. So the entire puzzle here is going to be how to figure out how to press that button. Which obviously it's on a wall, so we're going to need to have one of the expulsion tubes pressing against it to hold a block there. And yeah, getting a tube to press against it looks like, well, almost the easy part. If it weren't for that grill... Yeah, if it weren't for that grill, we could set something up there. Okay. So, what does this switch do? Okay, this cuts off that. Okay, so... And this switches its direction. Alright. So, let's first try... Let's get it so it lands on the launcher. Okay, now we have it basically being juggled. Yeah, it falls off, but... Okay. So, if we put blue there, orange there... Okay, that doesn't go all the way across, but we could put orange there. Alright, I'm starting to see the seeds of how we're supposed to solve this. So this is probably going to be one that we're going to have to think carefully about, figure out bits and pieces as we go. But, so for the first bit, we drop the block down, it gets caught while it's repelling, we turn it off, it gets launched up, then we turn it back on, it gets caught in the blue there. And then that'll rest against the edge, give us a bit of time to think. So let's just go ahead, do that. Okay. So now, step 2. Yeah, if we want, we can always reverse the flow to reorient it. That's not hard. Okay. So if we reverse the flow, there are 2 things we can do. 1, we can just let it drop. Or 2, we could do a vertical funnel there. I'm not sure if a vertical funnel actually benefits us. I think we can just let it drop into another funnel. So I'm thinking is we reverse this, change it while it's going. So actually, I don't think we even need to reverse it first. We can just, yeah, put the funnel there and then reverse it when we want it to get moving. Okay. So once we reverse it, it will move over to the right. And then we can move a bit to the left like that. And then once it's roughly in the middle, we can shoot down, catch it in a portal going up. Like that. There we go. Okay. And then, let's see, there is this thing. I don't know what it does. We might just have to test it. But we can very easily create a funnel going left. So before we do that, it's possible when we hit that, it's going to ruin things somehow. Not entirely sure. But yeah, maybe that destroys the block that touches it. We might have to find out. So let's just see what happens. Huh. Okay, that comes out to collect and hold any block that's there. That's interesting. Alright, so in any case, the next two steps for this, one, we reverse the portals, get it over to the right side, and then change the portal so it's coming out of there. That'll hold it up. Then we unreverse them, block gets pushed down, and on that switch, which undoes this extraction grill. I don't want to do that yet, because my gut says the fact that it's being held in place there is going to be important, as that will keep it held in place in the future so that we can collect the future block. Okay. Now, the time travel part is where the plan gets a bit difficult. So for the ultimate solution, we are going to need 2 blocks. We're only going to be able to solve this in the present after we bring the future block back to the present. And that's really the tricky part. Because once we bring the future block back, we can't do anything with the present block without destroying the future block. So, how do we do that? Yeah, how do we affect the block at all? Because right now, it seems like... Well, okay. If we turn off all of the expulsion funnels, the block is going to drop straight down into there. So if we wanted, we could, set up portal of one color here, other color there, and it'll drop in and come out. So we can collect the block that way, and we could perhaps put it back the same way. Alright, my gut is telling me, we should do that now. I'm not sure it's the final solution, though, because almost whatever we do, I can't think of a way to just place the present block and leave it for the rest of the puzzle. So I think the place that is going to be the safest to leave the present block is over on that switch, as that is one of the final places, final positions of the puzzle. And it does look like we can extract the future block from there. So let's reverse over, catch it there, unreverse, and push it down onto the switch. And then once it's there, we'll just let it settle. Okay. So that allows us to place a portal here if we so choose. And now I'm just thinking, yeah, once we have a portal there, even if the grid goes back up, it's not going to destroy the portal or the expulsion funnel. So it is possible that the final solution will not involve a block sitting there. Though that does get a bit tricky. Yeah, I'm just wondering, but yeah, I suspect the solution is going to be in the present. So anyways, let's go to the future. And then we will play around to move the block over to the left a bit, which is where we'll be able to collect it and bring it to the present. Okay. And actually, there isn't a grid there, so I could just drop it, set up like an orange there, and it'll just come straight out, and I can yoink. Okay, there we go. So, you are coming with me. Okay, so now the question is, how do we get this up there? Well, getting it up there is easy, just, portal, put. I just want to see, can we leave it to, like, rest on the edge there, because that will make things a bit easier.
In the event that something horrific were to happen to this facility in the future, my protocol is to find a viable candidate that can withstand the effects of time travel on the human body and help to rectify whatever led to the tragic events of the future. That's where you come in. We need you to stop this test subject dead in its tracks and save the facility.
Oh yeah, I feel very heroic doing all of this. Okay, yeah, so we can just leave it like that, which will let us switch around the portals, put the blue over there, and push that out and across, hold it, and hopefully solve the puzzle. Yes. Okay. But that's boring. I want to see if I can solve the puzzle in the wrong timeline, because they must have been expecting us to solve this in the present, where we have the two blocks. But if I leave the orange there and go to the future, it'll still be there. Oh, yeah, we can't put the block through the emancipation grid. That's what it's called, because if we put it through, it'll get destroyed. So, yeah, that's why we can't solve it in the future. Okay. There might be a way around that. My gut says this is one that could potentially be solved in the future, but yeah, let's just go with the intended solution. And there we go. Okay, so looking at the timer for this recording, it's kind of borderline whether I should go to another test chamber or not. So I think I'm going to head through, clone myself, and then kill the old clone. And then instead of going into the next chamber, I'll expand a bit upon some of the physics I alluded to earlier in the episode. Alright, so earlier in this episode, I talked about the uncertainty principle. So let me explain to you what exactly that is. So let's say we have a particle, and we want to describe where the particle is and what it's doing. Now let's say this particle exists in a one-dimensional universe for simplicity's sake. There are, in that case, two properties of note to describe momentarily what the particle is doing. There is its position, which we'll call x, and its velocity, which we'll call v. Now, from a quantum mechanics perspective, what we actually care about is its momentum rather than its velocity. So we will say its momentum, which we calculate by multiplying it by its mass, and we'll call that the letter p. So for any given particle, we have two properties we care about. Its position and its momentum. And if you want to get its speed from the momentum, you just divide it by the mass. So, what is the uncertainty principle? Well, the uncertainty principle basically says that there's a fundamental limit to how accurately you can know both the position and the momentum of the particle. So, putting it in scientific terms, which, don't worry, I'll explain this later, the uncertainty principle says sigma x times sigma p, here we're using implicit multiplication here, just putting one variable beside the other, is greater than or equal to the value h bar over 2. Okay, so let's explain this equation here. Let's start with the right side, as this is the easy part. H bar is called the reduced Planck's constant. If you've heard of Planck's constant, H bar is equal to Planck's constant, the letter H, divided by 2 pi. Really, all that you need to know on the right side is that this is a constant value, that nothing in the system affects it. Nothing we do in the universe affects it. This value is just hard-coded into the source code of the universe. Also of note, this is extremely small. So it doesn't come up in day-to-day activities, but it is non-zero. Okay, so what about the left side? What does the sigma mean? Well, the sigma is, roughly speaking, the uncertainty in something, or the statistical deviance of it, if you want to get a little bit more technical. So sigma is used traditionally to mean the standard deviation of something. So for now, let's just say that's uncertainty, then I'll go a bit more into the details later. Okay, so what this equation is telling us is that the uncertainty in the position multiplied by the uncertainty in the momentum of any given particle is always, at all points in time, all points in space, whenever we look at it, whenever we do anything to it, always going to be greater than or equal to this constant small value. So what does this mean practically? Well, practically it means that if you want to reduce one of these, you can only do so to a certain extent before you have to increase the other. So let's clear the screen and let's just talk about uncertainty and what it actually means. Okay, so let's just give a brief overview what the uncertainty of X is. If you've done statistics, you know what standard deviation is, you can skip over this. So let's say we have a particle, we don't know where it is, but we know it is probably close to point 0. And we've got a number line of all the points it could be at. It's probably close to here. It might be a bit to the right, it might be a bit to the left. On average, it's going to be above 0. If we were to look at this, reset the universe to re-randomize things, look at it a million times, add up all the positions, average them, the average will be close to 0. But any given time we look at it, it might be a bit to the side. We might find it off to the right, we might find it to the left, we might find it way to the right, way to the left, close, could be straight in, a bit off. There's a whole lot of points it could be at. And so what the uncertainty is it's basically giving you a typical distance that the particle will be found from its average point. So if you have a cloud that looks something like this, you can think of the standard deviation as being, okay, what's the average distance away? Now, properly speaking, it isn't quite the average. distance away. It is, if you really want to get mathematical about it, it is the square root of the average of the square distance away. So, actually, no, that's sorry, wrong notation. That's the absolute value. So, what this notation is saying is basically you take all the distances away for all of the trials. For each of them, you square them. Then you take the average of all those squares, and then you take the square root of that average to get the typical distance away. That's how this is defined. But all you really need to know is sigma x is the typical distance away from its average position. And similarly, sigma p will be the same except for momentum. Okay, so let's remind you the equation we're working with. We have uncertainty in x times uncertainty in momentum, which directly translate into uncertainty in velocity, is at minimum this small constant value of the reduced Planck's constant, which if we're just speaking casually and quickly, we call h bar because it's the letter h with a bar through it, divided by 2. So this has been calculated through quantum mechanics. I'm not going to go into proving it here. I'm just going to tell you what it means. So what does this mean? Well, practically speaking, it means that there is a limit to how accurately we can simultaneously know both the position and the momentum of something. So let's say you want to reduce the uncertainty in the position as much as possible. So let's say you want sigma x to be a very small value, let's say 1 times 10 to the ridiculously small 10 to the negative 99. So basically this is scientific notation for writing a 0.89 zeros and then a 1 meters. So we want our sigma x to be ridiculously, obscenely small, even by quantum mechanics standards. It is as small as we can imagine. Okay? Well then, what does this equation at the top tell us? Well, we can just rearrange the parts of this equation to tell us something about the uncertainty in the momentum. So that means sigma p is going to be greater than or equal to, we just divide each side by sigma x. So sigma x times 2, or we can put in the values, h bar divided by, 2 times 10 to the minus 99. Oh, but you might know that if you have a negative exponent in the bottom of a fraction, you can make that a positive exponent in the top. So you could have h bar times 10 to the positive 99 up here divided by 2 meters. So when we want this ridiculously small uncertainty on position, that's going to turn out to, oh, we've got a pretty big uncertainty on momentum. But now we're in the regime where it actually matters how small h bar is. So we're going to need to get some actual numbers for that. So the actual value for h bar is, roughly speaking, 1 times 10 to the minus 34. I told you it was ridiculously small. And the unit, it's typically given in our joule seconds, which a joule second isn't actually the most useful for us. Probably the most useful way to write the unit would be kilogram times meters squared divided by a second. Yeah, this is a constant that we're using for calculations, and it goes into a lot of things. So the units of the constant itself don't always make direct physical sense, but what comes out of the equations will make sense. So let's put this back into our equation here, and we'll get that value. So our greater than or equal here, sigma p is greater than or equal to. So on the top, we're going to have 1 times 10 to the minus 34 times 10 to the 99. So when you're multiplying things with different exponents together, you add up the exponents. So we add 99 and minus 34, or 99 minus 34 is 65. So we get approximately 10 to the 65. And then we'll have our units here, kilogram meters squared per second. And on the bottom, we have 2 meters. So we can cancel out the units a bit. We'll cancel off the square on the meters and the 2 there. So our simplified equation, putting everything together, is that the fundamental limit for uncertainty in momentum is 0.5 times 10 to the 65 kilogram meters per second. So let's put that into context for how big this is. This is already, we've got a huge exponent here. So this means, like, okay, well, first of all, how much does our particle weigh? Let's say our particle weighs 1 kilogram, to keep things simple. That means our uncertainty in its speed is 10 to the 65 meters per second. For comparison, the speed of light is about 3 times 10 to the 8th meters per second. So this is 57 orders of magnitude greater than the speed of light, which is to say that the momentum of it could plausibly be anything in the universe. It's not actually going to be greater than the speed of light. That's about the only limitation. But relationship between speed and momentum actually changes a bit as you approach the speed of light. So basically what I'm saying is, you try to narrow down the position of this particle to this much, its momentum is going to be whatever the hell it wants to be. It wants to be going basically the speed of light. It's going to be going basically the speed of light. So what does this mean, and what does it have to do with lasers, which is the context I actually brought this up in the first place. So we'll clear ourselves up and just start with this equation again. So what is a laser? A laser is basically saying that we want to have waves of light coming out of a thin opening. So basically, imagine this is all filled with light, and light will be in there bouncing around. We want to do something to it so that all of the light coming out will only come out through a thin opening here. So like put a little end here, but still light might be coming out of it at multiple different angles. So let's say it's reflective in here to keep the light contained but without losing it, but we want it to escape through a thin opening. So we'll create a very thin, very long opening. This is kind of a simple way to create a laser. It's not how actual ones work, but we don't want it to bounce through sideways. So here, instead of this part being reflective, we'll make it absorptive, so that you can imagine, you know, light can bounce around in there, but any light that goes through this opening, if it ever hits the wall, it gets absorbed by the wall. So the only light that can get through the opening is light that's going basically straight through. So the result of that is that light that comes out will be going basically straight. But with this type of opening, there's already a bit of a limit that you don't want, that you could have it going from an angle like a bit down to a bit up. I'm exaggerating here, but it could come up like that. It'll still be focused more than you initially had, but it will spread out a bit. But that isn't actually what limits how tight a laser can be. So let's zoom in on our opening a bit. So this is just zooming in on this part. And let's think about the light as it goes through here. So as the light is coming out, what's actually going on is that we've limited its position. We've said that the position of the light, at least in the y dimension, is limited to being in here. So basically the size of this is going to be, broadly speaking, some multiple of sigma x. So let's say, actually, let's not put that 2 in there. Let's just use rough approximations. Let's say that this distance is going to be approximately sigma x. So some small multiple of it. We don't need to worry about the specifics to highlight things here. So when we have a laser that works like this, we're compressing the exit pupil of the laser to some diameter, and then the sigma x of the light, at least perpendicular to this, is going to be proportional to that diameter. So as soon as we do this, this is going to have an effect on the momentum of light in this dimension. So this means that we can go back to our equation up here and say that uncertainty in the momentum is greater than or equal to h bar over d. We're ignoring these rough constants right now. So what this means is that vertical momentum of the light, now light is weightless, it does have momentum, but you need to use a bit of relativity to calculate what it is. This means that the vertical momentum of the light, that is how far the light is traveling up or down, is going to be, at minimum, this small value of h bar over d. But the smaller you make d, the bigger this uncertainty is. So there are a couple things you can do. You can have a big exit pupil for the laser and low momentum uncertainty, or you can have a small exit pupil and big momentum uncertainty. Either way, you aren't going to be able to make the laser infinitely thin. Okay, let's take this back to our laser example. We've got a small distance, d there. Let's say very small, 10 to the minus 10 meters. Then we plug it into our equations. We get uncertainty in momentum is greater than or equal to h bar over 2. We're skipping the 2 there, times 10 to the minus 10. That gets flipped over. We put it back up on the top. H bar times 10 to the 10 meters. So what does this mean practically speaking? Well, we want to relate it to what the light is actually doing, and there are a few useful equations we can use. One of the most is that the momentum of light is equal to Planck's constant, not reduced, divided by its wavelength. And let's say we just have a ray of blue light. A typical value for light that might be visible could be around a few hundred nanometers. So let's say the ray of light is 600 nanometers, which is equal to 6 times 10 to the minus 7 meters. And again, we're just going to round to the nearest order of magnitude. I'm just making a point here. So 6 closer to 10 than to 1. So we'll say this is approximately 10 to the minus 6 meters. Okay? So putting this up here, bring that on the top, we have h times 10 to the 6 meters. Okay, so what about the uncertainty here? So let's look at these two values. So h bar is close to h. It's like roughly 1 order of magnitude less. So if we want to just correct these so that they're both in the same unit. We could change this to h bar there and add an order of magnitude here. So this is about h bar times 10 to the 7 meters. Don't worry too much about the specific values. We're just illustrating things here. So for a ray of blue light, its momentum, going straight out of the aperture is about 10 to the 7 meters, but the uncertainty in its momentum is 10 to the 10 meters. So this means our uncertainty in its momentum is 1,000 times as large as the overall momentum it has. So if we try to squeeze the pupil this small, then yeah, we can get it to exit a small level, but quantum mechanics says that even if we think it should be coming straight out, no, the uncertainty principle rules the day, and the uncertainty principle says that when you have something coming out of an aperture like this, whatever you think it was doing coming through, the second it goes through this, the uncertainty principle comes on and it can shoot out in any direction it wants. And what actually ends up happening is the smaller the aperture you have, the greater the spread. So that is to say, if you have a wide aperture, you'll spread out a bit. You have a smaller aperture, you'll spread out a lot. And you have to have a teeny tiny aperture, you'll spread out a ridiculous amount. So when we try to make our subatomic aperture, we get the light going basically anywhere. It essentially comes out of the aperture in a flat sheet, doing whatever the hell it wants. So this gives us a problem if we're making a laser, that none of these options have a thin focused ray of light. With a wide aperture, it spreads out a little, but it started pretty thick. With a small aperture, it starts thin, but then spreads out a lot. So if you want a laser that, like, let's say you were looking 1 meter away. So let's say we have a 1 meter distance out here. Then we're looking at the spread. There's going to be some fundamental limit that there is no way to get the laser to focus tighter than that fundamental limit. Then it actually turns out this depends a bit on the wavelength of light, what that limit is, and I'm not going to go over the calculations because it doesn't really matter what the specific limit is. But this is the problem we have with lasers, that there is, physically speaking, no way to get a laser to perfectly focus. Whew, okay. That was a lot of math and science, but I hope you found that discussion of...
To the final chamber. Don't get overwhelmed.
Excuse me, I was talking here.
One step at a time, and you will soon find the solution.
Yeah, we can do that next week, okay? Yeah, anyways, I hope everyone found the discussion of lasers interesting, and I will see you all again next week for the final chamber of Portal Reloaded. And maybe there'll be something more after that. See you all again. Bye-bye. Thank you very much for watching, everyone. If you enjoyed this video, please leave a like, subscribe, and click the bell to be sure you get notifications of new uploads. See you again soon. Thank you very much for watching, everyone. If you enjoyed this video, please leave a like, subscribe, and click the bell to be sure you get notifications of new uploads. See you again soon.